In this video, I want to look at hypergeometric distributions, which are very similar to binomial distributions. There's only one difference between the two. For hypergeometric, let's suppose we take a random sample of size little n, taken from a finite population of capital N units. Let's suppose a number, m1, of the population have some given property. The rest, m2, which is n minus m1, do not have the property. So the main difference between the binomial and the hypergeometric is independence. In a binomial distribution, all of my experiments, all of my individuals, were independent. However, here we don't have our independence property anymore. We then have the number of x units with the property in the sample is a hypergeometric random variable. Some examples of this, let's suppose we have a batch of 100 products. We want to know how many are defective. Or we might look at the number of Democrats in a small town. We might also look at the number of Democrats in a small town or the number of red cards drawn from a deck. The idea being that the successive trials are no longer independent. So the PMF, the probability of x, is equal to combination m1cx, m2cn minus x, all over m1 plus m2cn. And we say the probability is 0 if x is greater than m1 or n minus x is greater than m2. In this case, the mean, or the expected value, is n, the number of successes that we want, times m1 over capital N, our total sample size. And the variance, little n, times m1 over n, times 1 minus m1 over n, times big N minus little n over big N minus 1. Let's suppose that 12 refrigerators have been returned to the distributor because of a high-pitched oscillating noise. We're then going to suppose that 4 of the 12 have a defective compressor and the rest have less serious problems. 6 refrigerators are selected at random for problem identification. We're going to let x be the number of those found with a defective compressor. We're going to find the sample space of x, the value p of x equal to 3, as well as the expected value and variance. So let's start by going through our problem. We have a total of 12 refrigerators. So this is the total size of our population, capital N. We know that 4 of the 12 have a defective compressor. So this is our value for M1. And the rest have less serious problems. 6 of the refrigerators are selected at random for problem identification. So that tells us our size of little n. Since we have a total of 4 of the 12 that have a defective compressor, the possible number of ones that have a defective compressor, well, we could have 0, 1, 2, 3, or 4. These are the possible values of x. We can see that we could have 0 with a defective compressor and 6 without. We could have 1, 2, 3, or 4 with a defective compressor and the corresponding number to add to 6 to be less serious problems. So this is the sample space. The next thing I want to find, the probability that x is equal to 3. We said m1 was equal to 4, so we're going to do 4 choose 3. We then have the rest. If 4 out of 12 had a defective compressor, 8 did not. Choose n minus x, so 6 minus 3 is 3. So what we're doing here is we're choosing 3 out of the 4 defective and 3 out of the 8 not defective, since this is what we want. We want 3 defective and 3 not defective, since we have a total of 6. We then need to divide by 12, choose 6. Since this is the total number of things we are actually, the total number of possible combinations we have. This gives us 0.242 approximately. So the probability of having 3 defective would be approximately 0.242. The next thing I want to find is the expected value and the variance. The expected value is little n times m1 over big N. So the expected value here is 2. We would expect to have about 2 defective with a defective compressor. And then my variance, little n times m1 over capital N times 1 minus m1 over capital N minus little n over capital N minus 1, which gives us approximately 0.727. So the variance is 0.727. Let's suppose a forest contains 30 elk, of which 10 are captured, tagged, and released. A certain time later, 5 of the 30 elk are captured. We want to find the probability that 2 of the 5 captured elk are tagged. What assumptions are you making? So let's start with this probability. We have a total of 30 elk, so that would be my value of capital N. The fact that 10 are captured and tagged gives me M1. And we want the probability that 2 of 5. So 2 is going to be my value of X, and 5 will be my value of little n, the total number that we're getting and the total number of successes we want. So the probability that X is equal to 2, well, out of the 10 that are captured, we want to pick 2 of those. That means out of the 20 that were not captured and tagged, we want to pick 3 of those. Out of a total of 30 elk that we are getting 5 of. And this is equal to approximately 0.36. So what assumptions are we making? We are making the assumption that it is equally likely to capture any of these elk whenever we capture the elk to figure out how many are tagged. Let's suppose a small voting district has 101 female voters and 95 male voters. A random sample of 10 voters is drawn. I want to find the probability that exactly 7 of the voters will be female. So the district is 101. That's going to be capital N. So in this case, my capital N will be the total number of people I have, 101 plus 95, which is 196. M1, we have 101 female voters. And we want the probability that exactly 7 will be female out of a total of 10. So my little n is equal to 10, and X is equal to 7. Since this is the total number of people that I'm going to look at, and 7 is going to be the number that I want to be female. So we have the probability that X is equal to 7. Well, out of the 101 females, I want to pick 7 of them. And then out of the 95 males, I need to pick 3 of them to get to a total of 10. Over, out of the total 196 people, I'm going to pick 10. And that works out to be approximately 0.13. So there's a 13% chance that exactly 7 of the voters will be female.